Before we dive into today's episode, make sure to hit that subscribe button. It's the best way to stay updated with our latest insights.
Ladies and gentlemen, welcome to the CISC Academy podcast. The energy is electric. The crowd is alive. Let's dive into greatness. We're champions strong.
Before we start the show, don't forget to check our new ebook, Kill All Bugs, Learn Software Testing in One Day. For a limited time, it's only $9.99. Links in description.
Welcome back to the Deep Dive. Today, we are strapping in for a fascinating journey right to the very core of computing. We're diving into the architecture that basically dictates how efficient, how powerful, and how smart every electronic device you own truly is. We are talking RISC versus CISC.
The big one.
It is. You sent over this incredible stack of sources comparing these two fundamental philosophies, and our mission today is to just cut through all the complexity.
There's a lot of it.
We're going to extract the essential high-impact knowledge, including a really surprising modern twist that, well, it changes how you think about Intel versus AR. This is your shortcut to being instantly well-informed.
And what's so fascinating here is that this isn't just some, historical debate. It's an ongoing fierce competition right inside the machine.
Okay.
It's that classic computing trade-off. Do you go for speed and efficiency through simplicity, that's RISC, or do you build maximum capability right into the chip itself, simplifying the software side? That's CISC.
And that choice affects everything.
Everything, from the size of the transistors to power usage to compiler development. It's fundamental.
Okay, let's unpack this, and let's start with those full names, because they really do tell you what we're dealing with. RISC is Reduced Instruction Set Computers.
And CISC is Complex Instruction Set Computers.
The names are kind of perfect labels, aren't they?
They are. They perfectly describe their core design intent, which, is heavily driven by historical constraints. Let's start with CISC, the older philosophy. It came about when computer memory was just incredibly slow.
And expensive.
And so expensive.
Yeah.
So the goal of CISC was simple. Make the compiler's job easier and use as little memory as humanly possible.
Okay, so if memory is the bottleneck, you want to do as much work as you can with every single instruction you pull from it.
Exactly. CISC aimed for maximal capability in the hardware. Instead of making a programmer write, say, 3 or 4 machine instructions to do a complex calculation.
Like what? Give me an example.
Calculating a square root distance, for instance, a CISC processor offered one single built-in complex instruction to handle the whole thing.
Wow.
It was the ultimate Swiss Army knife approach to computing.
So all that complexity gets moved out of the software and baked right into the physical silicon of the chip.
That is the defining feature. Now, contrast that with RISC. RISC was a reaction to CISC. It came along in the 80s when memory and compilers were getting much faster and smarter.
Okay.
RISC's design philosophy is the complete opposite. It's the ultimate minimalist approach. Perform a very small, primitive number of instructions, often less than 100.
And the goal there is just raw speed.
Pure speed. By limiting the instructions to only the most essential, simple steps, they can make sure the chip operates at a much higher clock speed with minimal execution time.
So with RISC, the performance is optimized with a heavy emphasis on the software.
Yes, the compiler, or the programmer, now has to do all the heavy lifting of breaking down that complex square root calculation into lots of little simple instructions.
I love the specific examples you pulled from the sources. They really ground the concept. The early CISC machines were those big, powerful systems like the PDP-11 and the DEC systems, right? The ones that really dominated the early computer world.
For sure. And the success story of RISC is literally everywhere you look today. We're talking about ARM, Spark, and Mixis architectures. ARM especially powers pretty much every smartphone, tablet, and portable device on the planet.
And it all comes back to that fundamental trade-off between instruction capability and sheer speed.
It determines everything.
All right, now we get to the real technical deep dive. How do these two different philosophies actually handle instructions and execute code inside the chip?
Well, the key difference is standardized versus variable input. For RISC, the instruction set is reduced, it's primitive, it's simple, and this is crucial. It follows a fixed instruction format.
A fixed format.
Typically 32-bit, Think of it like a fixed-size Lego block. Every block is the same size, which makes decoding it instantaneous and really, really simple.
And CISC, with its giant library of powerful commands.
Well, CISC has a huge instruction set, and those instructions are variable length. They can be anywhere from, say, 16 bits to 64 bits, or even more, depending on the command's complexity.
So the chip has to work harder.
The decoding logic becomes highly complex. The chip has to first read the instruction, figure out how long it is, then determine what it's supposed to do, and then execute it. It's just so much slower than the fixed format approach.
And here's where it gets really interesting, in terms of the execution unit itself. Let's talk about that critical difference between hardwired and microprogramming.
This is absolutely fundamental. RISC, with its simple, standardized instructions, uses a hardwired unit of programming.
Meaning?
Essentially, the chip is physically designed to process that limited set of commands instantly. There's no middleman. And that is what allows RISC to achieve that coveted metric. One instruction per clock cycle.
One instruction per cycle. That's the speed advantage right there.
It is.
And CISC, with all its internal complexity, it needs that translation layer, doesn't it?
Yes. CISC uses what's called a microprogramming unit. This is a permanent, separate memory area on the chip that contains these tiny little programs, the microcode.
Okay.
So when the CISC chip gets a complex instruction, like that single square root command, the microprogramming unit acts as an on-the-fly translator. It takes that one complex command and breaks it down into a whole sequence of simpler internal steps.
So because of the complexity, a single instruction from the outside might take, 10 or 20 steps on the inside?
It could, which means it takes several clock cycles to complete. It might save memory, but it definitely costs time.
And that's why the clock time for different instructions on a CISC machine is never the same.
Precisely. The process is inherently variable and, well, slower.
Let's move to memory access, specifically registers. This is another massive architectural split, and it explains a lot about why RISC is so power efficient.
Absolutely. RISC processors are designed with multiple large register sets. We're talking sometimes hundreds of general-purpose registers right on the chip itself. They emphasize register-to-register operations. They try to keep the data they're actively manipulating inside the chip as much as possible, operating on that internal memory pool for max speed. In fact, RISC only allows memory access for two specific instructions, load and store.
Everything else happens inside.
Everything else is internal.
So it's like keeping all your tools and materials right on the workbench instead of having to run back and forth to the storeroom every 2 seconds.
That is a perfect analogy. And CISC, historically, has only a single register set, or at least far fewer general-purpose registers. Operations often need to be performed in memory itself, which means the chip has to constantly talk to the slower external RAM.
So that constant back and forth adds up.
It contributes to the overall longer execution time.
All right, let's talk about performance optimization, the engine of modern speed pipelining. This seems to be the single biggest reason why RISC dominated the speed metric for so long.
Pipelining is absolutely critical. Think of it like a factory assembly line. If every single item coming down the conveyor belt is identical, fixed length, fixed complexity, you could just feed them through in rapid succession.
One right after another. High throughput.
Exactly. That's RISC. Because RISC instructions are fixed length and take one cycle, they are just perfectly suited for feeding through a deep pipeline. RISC processors are therefore highly pipelined, which is how they get such staggering performance from simpler instructions.
But with CISC, if an instruction can be 16 bits 1 second and 64 bits the next, it's like throwing huge, unpredictable parts onto that smooth assembly line.
It jams a line. It completely jams it. Because CISC instructions are variable length and multi-cycle, pipelining them is either extremely difficult or it requires this tremendous amount of extra complexity.
Like adding logic that has to guess how long the next instruction is?
Right. So historically, CISC was mostly less pipelined, or not pipelined at all, which just severely limited its performance compared to RISC for years and years.
Okay, let's shift into the trade-offs and practical consequences, because both approaches have some pretty significant catches. Let's tackle the RISC problem first. This idea of compiler dependency and code expansion.
Right, the RISC catch. While it's fast, its performance depends almost entirely on the genius of the programmer or the compiler.
Okay.
Since complex tasks have to be broken down into so many simple steps, the compiler needs to be incredibly smart to order those steps perfectly to leverage the pipeline and registers efficiently.
So a mediocre compiler means mediocre performance.
It suffers dramatically.
And then there's that notorious code expansion problem. What exactly does that mean for someone listening?
So imagine that single complex CISC instruction takes, say, 1 byte of memory. To do the same thing using primitive RISC instructions, you might need 4 or 5 instructions.
So 4 or 5 times the memory footprint.
Exactly. The code itself gets bigger.
And that has consequences.
2 big practical consequences. First, it relies on heavier use of RAM. And second, it fills up the instruction cache much faster. And even though RISC chips operate on the cache and registers, if the code base gets too large, the processor has to constantly go back to slow main memory to get new instructions, and that creates bottlenecks.
That transitions perfectly to the CISC complexity issue. If CISC is so complex and so slow to pipeline, why on earth did it win the desktop war? Why do Intel and AMD still dominate the server market?
2 words. Backward compatibility. New versions of CISC processors have to contain all the earlier generations as a subset. This commitment means you can still run software written decades ago, which is a massive, massive business benefit.
Yeah.
But the hardware and the instruction set just get perpetually more complex.
Legacy compatibility at the cost of continually increasing hardware complexity.
Yes.
But here's the huge aha moment that your sources really emphasize. This is the only reason CISC is even competitive today.
Right. We have to introduce the concept of micro-operations, or MILOps. Yeah. Around the mid-90s, when RISC chips started significantly outperforming CISC chips because of pipelining, Intel and AMD had to adapt. They couldn't just abandon backward compatibility.
So what did they do?
They implemented a new architecture internally. Modern CISC processors, your BIAS6 chips, now have a translation layer. When a complex CISC instruction enters the chip, it is immediately broken down into a sequence of smaller, fixed-length, RISC-like instructions.
Wait, hold on. So you're telling me that today's dominant CISC chips are essentially RISC chips wearing a CISC mask?
That is exactly what the sources confirm. The CISC instruction set is basically a user-facing translation layer for backward compatibility, but the actual high-speed execution core inside the chip is highly pipelined, and it uses simplified fixed-length instructions. It behaves functionally like a RISC processor.
That flips the entire script.
It does. It's the great convergence of the 2 philosophies.
And that explains how they managed to get modern speed while keeping that critical legacy function.
It let them achieve high instruction per cycle rates and use deep pipelining. But the cost is still there. The hardware logic needed for this complex decoding and translation layer is massive.
Which leads to bigger chips and higher power consumption.
Exactly. And that brings us to the final key difference: cache design.
Right.
We noted that RISC often separates data and instruction caches. This is called the Harvard architecture. CISC typically uses a unified cache, the von Neumann architecture.
And why does that matter in the real world?
Well, if you separate your instruction cache, your recipe, from your data cache, your ingredients, the processor can fetch the next instruction and the next piece of data at the same time.
Oh, simultaneously.
Yes, which significantly helps the RISC goal of 1 instruction per cycle. A unified cache, like in CISC, has to share access, so it's often fetching things one after the other.
So the RISC way is faster.
It's faster, but it can also lead to cache space being wasted if one side, say the data side, is much larger than the instruction side, or vice versa.
That really brings so much clarity to the architecture. The efficiency of RISC is just designed into every single layer, from instruction size to the cache layout.
It's a complete philosophy.
Okay, let's quickly wrap up with a real-world application roundup just to cement these concepts with the devices you use every day.
For sure. The modern CISC success story is still the Intel x86 CPU family and AMD processors. They dominate high-power computing. Servers, desktop workstations, complex security systems, anywhere that raw computational grunt and backward compatibility are absolutely essential.
And the dominance of RISC, mainly ARM, is all about mobility and efficiency. So smartphones, PDAs, embedded systems, and now increasingly specialized data center chips where energy efficiency is the most important thing.
It always boils down to your priority. Are you prioritizing maximum compatibility and instruction power, which is CISC, or maximum energy efficiency and speed through compiler optimization, which is RISC?
So let's synthesize all this. What does this deep dive mean for you, the person listening, trying to understand the engine that's powering the tech in your life?
The key takeaway is that modern reality, the philosophical war, forced a technical convergence. RISC excels where simplicity and speed are paramount, and it's still the design of choice for anything that needs long battery life.
Right.
CISC is indispensable for tasks requiring comprehensive command sets and that legacy support. But you have to remember, the performance gap was bridged because modern CISC is RISC on the inside. It gets its speed by translating complex instructions into simple weeps before execution.
So performance is optimized with brilliant software for RISC.
And incredibly complex, high-power hardware for CISC.
Understanding this hidden battle really clarifies why certain devices, like your phone, are so remarkably fast and cool running, that's RISC's efficiency, while your powerful desktop needs that massive, power-hungry complexity layer to run decades of software.
Exactly.
Yeah.
And here's a final sort of provocative thought to take with you, building on that cache discussion. If modern CISC is already translating its instructions into RISC-like whoops on the inside, why does it still, for the most part, maintain that single unified cache structure of the old von Neumann architectures? In a world where devices are constantly needing to shift between high-speed data crunching and complex legacy tasks, is that unified cache now becoming the final, significant performance bottleneck for these high-power CISC chits?
Or is the benefit of having a flexible cache still not enough to overcome the cost of physically separating it?
Exactly. It's something to think about as you watch the next generation of processors hit the market.
Thanks for listening. If you found value in today's episode, please subscribe and leave us a review. It helps more people find the show. See you in the next one.
Hey, yo! Haven't you checked out our new book yet? Link in description.
CISC.